Hello, welcome to my next video. Today we're going to practice some more organic equations. And the next on the list is the electrophilic addition. So first of all, I think it's worth to mention what this phrase actually means. So first of all, electrophilic. Electrophile is a species which loves electrons. It's basically an electron-loving species. Therefore, it doesn't have enough electrons already. It has low amount of electrons. It wants to gain more electrons. It loves these electrons. And addition just means adding on. So basically what this reaction means is we add in an electrophile into a compound. So I created an example for you. Actually, I'm going to draw it for you down. It's using ethane. Ethene has its double bond, so it's ethene. Ethene has a lot of electron density around here because we have these pi electrons orbiting. They form these pi orbitals. In these pi orbitals, we have a lot of electrons. We have a lot of electron density. It's very negative double bond. And as we know, electrophile wants to get these electrons. So if we put, this is an example of electrophile. HCl is an electrophile. HCl is polar. It's polar because the electronegativity difference between hydrogen and chlorine is big. Chlorine is more negative, therefore it's going to be slightly negative, and hydrogen is going to be slightly positive. Don't worry if you don't know which compound which would be an electrophile. You always get it in your question. You may be asked to draw the mechanism, which is what we're doing right now. And whenever you get something that has to be added, this is going to be polar. So we have chlorine, which is negative, hydrogen, which is positive. There is too many electrons here. Therefore, the electrons go to our hydrogen. Hydrogen slightly plus is here our electrophile. It's no longer the whole compound. We're using this whole compound as an electrophile. However, only the hydrogen becomes the electrophile that's going to be added on. And this is because it's slightly positive. So it's electron loving. It wants to attract these electrons. These electrons are attracted from the double bond. This arrow shows the movement of these electrons. Here we have a heterolytic bond fission. Heterolytic bond fission means that one of the elements get more electrons than the other. In this instance, is chlorine is more electronegative. It gets a greater share of these electrons, and I'm going to show these greater share of these electrons. Hydrogen becomes slightly positive. It wants to gain these electrons again, so it's gaining them from the double bond. I think that makes sense now. So we go in further down. We still have two carbons. It's no longer a double bond because we just shared these electrons with our hydrogen. We have one hydrogen more. We have 5 on here. This is a hydrogen. That hydrogen bonded with our ethene and it became a carbocation because now we have a positive carbon. However, we also have this chlorine, which becomes completely negative. Hydrogen told them, go away. I'm going to bond to this ethene. I don't need you anymore. You can go away. So our chlorine minus is floating around with its electrons. Carbon on ethene becomes positive because we included another hydrogen which was positive, so taking electrons away from the carbon to hydrogen, carbon becomes positive. Therefore, chlorine wants to join in with the carbon. Carbon is lonely, carbon doesn't have electrons, it's positive. Chlorine is negative, it's also lonely, so it's going to go in this place. Therefore, what we form at the end, all the hydrogens, and on here we have chlorine. That's also how you form a halogenal alkane. So you can either do halogenation or electrophilic addition. So I'm just going to quickly run through it again. We have an ethene, it's a high electron density. We have a compound HCl floating around. Chlorine is more electronegative than hydrogen, therefore it gets a greater share of the electrons. It takes these electrons to itself. Hydrogen becomes slightly positive, chlorine becomes slightly negative. Ethane has too many electrons, so it gives these electrons to hydrogen. Hydrogen is being added to the compound and says goodbye to chlorine. I don't need you anymore. I have my ethene. It joins the molecule. Chlorine becomes on its own. Carbon becomes slightly positive because we added a positive hydrogen to the compound. Chlorine says, oh, I'll share these electrons with your carbon, so it joins the carbon. We have a halogenal alkane. However, there is also an instance where you can add Br2 or Cl2. But we're focusing on Br2. That's the one you need to know for your exam. So again, we have this ethene floating around, but instead of our HCl, we have Br2, so two Brs. They both have the same electronegativity values. Therefore, this molecule is not polar. However, when it gets close enough to our ethene with high electron density, it pushes away these electrons from the bromine that is closer to it. So this bromine is closer to our ethene, and ethene has electrons, so it pushes away these electrons towards the other bromine because it repels these electrons. Therefore, the lower bromine becomes slightly negative and this one becomes slightly positive. The electrons move down because they are repelled by the electron density. So again, the same thing happens now. One of them is slightly positive, one of them is slightly negative. These electrons go to the bromine that's slightly positive. Our bromine slightly positive becomes an electrophile. It wants to attract electrons. It's electron loving. So these electrons move to this bromine. It's no longer an alkene. It becomes an alkane again with a positive carbon. A compound with positive carbon is called a carbocation. Cation. It's positive, but we have this bromine floating around, and carbon is positive, our bromine is negative, so it's going to go onto our carbon, and again we form a halogenal alkane. These bromines you can put either here or here or here or here, it doesn't matter. You can just put them anywhere. This reaction is actually a test for alkanes. Alkenes. If it's an alkene and our bromine joins the compound, the color of the solution will go from orange to colorless. However, if it was an alkane, the color wouldn't change. Lastly, we have instance where we have hydrogen. So we're not forming halogenal alkanes now, we're just adding hydrogen. Again, we have our ethene at the very beginning. We have hydrogens. The same thing happens, the negative electron density repels these electrons, so they go down to our second hydrogen. So that one becomes positive, this one becomes negative. Again, the electrons go from our double bond to our positive, slightly positive hydrogen. Then we form an alkane with a carbon cation. But what we got left is that hydrogen minus. It grabs onto that carbon and we form an ethane. As you can see, that's not halogen alkane, but that's also a electrophilic addition. That hydrogen becomes an electrophile and grabs these electrons, which are donated by the double bond. However, there are a couple of conditions you need to know for this reaction. The conditions are 70 atomic pressures, 200 degrees Celsius, and nickel. Nickel is the catalyst of this reaction. This reaction otherwise would be very, very, very slow. So we use a nickel catalyst. And just one more thing, this reaction is used to harden vegetable oils because we convert unsaturated into saturated compound. So this was all for this equation. I hope you liked it. If you did, leave the thumbs up, subscribe to my channel, and see you soon. Bye.